time to show my results. But at the beginning, I try to continue the morning session of the calculus. This is the result is result is pencil, some calculus and myself. So this is kind of the automated script with the time is kindly copy my script inside the account. Little bit different today. Today, I'm going to tell you about the script to combine all time entries with data. But this is just my creation script in comparison. It's the setting of the foundation. It works very fine and very nice too. So this is just a combination of the comment. Today I will talk about linear solver.
No. Hide. Okay. So you put on one. No. Go here. No, here. No. This was
small. So today my talk is about linear solver. So this is just research phase, not yet provide the software.
Yeah.
But this is idea of to use so-called mixed expression arithmetic. Now it becomes hot topic on the HPC community. But with my idea is bit doubtful to find the user of mixed expression. But here I will show some two advantages. We apply if we apply the mixed expression. First, I briefly review. I first briefly review the system. What system I should. So first we have to find the solution of D. This is derived by finite volume or boundary element. And only a system we start to automatically generated mainly by creating. And then we can write or we have to write linearization of the nonlinear system by implementing or graduate. Of course, with the intermediate stage, let's see under something of the in charge of this topic and linear solver. But finally, we have to solve the linear system, two linear system. And this is the with the recent years. What kind of the constant number is? Constant number for for example, mathematical stroke is 10 to the power 6. Because of divergence strings. Divergence string is different physics than momentum equation. So suppose the divergence number becomes large due to divergence strings. And also most of the highest constant number I experienced is the semiconductor problem. This is due to mathematical model of the three is something the diffusion parameter depending on potential, electrostatic potential. So there is some.
Yeah, the people on Zoom have difficulties hearing you, and so we want to put your sound in.
Try to put
I don't know why you put on join audio.
Because I put this. Because it's not make the having I put off the audience. What is the I have to
there you have the audio.
Yes, so you need just to join the audio, but I don't know.
You have to get out and to restart. So sorry.
Yeah, I'm mute.
Yeah.
Oh. No, sorry. No. No, it's I off the monitor, but
And you put
let's-
the audio here.
okay. So
Okay, but
okay.
we just need to sound. So I think because you are here.
No, so the next problem is okay.
Yeah.
Sorry. The problem of the semiconductors have very high constant number, and also plus the figure I showed 3 minutes ago, it was the kind of the pre-boundary problem. This constant number is moderate, and also the shape optimization we have to think about the constraint. In that case, its constant number is also become higher. And that means we still have the problem to solve the difficulty to solve the linear system. And that means we have to continue to use direct solver. That is only can handle the higher constant number. And then also we have technique of the iterative method based on the Kulak method, GMLess or CD. And then this possibility is to combine GMLess with the direct solver is used as precondition. So, but I said that there's some difficulty is appears in numerical estimation. Mainly comes from the numerical algorithms, not the completely physical one. A typical example is if I would like to use the domain decomposition method like SETI method. So it brings something the pseudo singularity inside the code, but we have to handle that. So then the question is how to tackle with such kind of higher constant number problem. So of course, this constant number is still higher, so it's difficult to solve by iterative method, and also if too much higher, we have to switch to the higher precision computation. Is the quadruplicity arithmetic. This is the global view of what I should do, and then next one is some details on the direct factorization solver. In this main key issue is the decomposition of domains into small pieces, and also introduce kind of pivot technology. Pivot technology provides us some kind of stability of the factorization. But in mathematical way, this equation is very simple. Just we only compute shell complement recursively. So this is definition of the shell complement. S22 is the shell complement, and then this is matrix is decomposing 2 blocks, 2 by 2 blocks, and S22 is computed. And the way to decomposition is this is based on this so-called nested dissection ordering. So it consists of several bisection layers, and the lowest layer is all the matrix is sparse, and then higher layer that is consists of the dense matrix thanks to the computation of S22. S22 contains a Fermat inverse, so even matrix A11 is sparse, the S22 becomes dense. So by this structure, we can employ +3 level +3 operators. So this is very fast in modern CPUs. So this dissection ordering is realized by Metis or Scotch. That is also we can use directly from the PFM, but this is used for the inside of the linear solver. Okay, so but next important issue is pivot strategy. There are several ways of pivoting, but I have not much enough time, so I only concentrated on myself to the so-called symmetric pivoting. This means this is very friendly to finite element framework because unknown functions and test functions is permutated in the same order. So it is very natural way for finite element solutions. But unfortunately, by this symmetric pivot, system may be singular if the matrix is indefinite. In that case, we can use a kind of mixing of 2 by 2 pivot technology. This technology is very old. It was invented by 1975, but this is still part 1. So I can factorize all stuffs, and this is a schematic figure in the whole figure, combining with nested prediction plus pivot technology. So first, here we have 7 submatrices with 3 layers, and 4 to 7 is the most lowest layer, and we can solve the direct solver is factored with this one. And then during factorization, using symmetric pivoting, some parts become quasi-singular. And that part is excluded from this tree. That is the idea, to separate the matrix, the easily factorized part and difficult, still hard to factorize. So this red part is postponed to the end, and the last shell component S22 is something gathering bad guys. So good guys is already factorized, is beaten by A11, is that is beaten by blue part, and postponed bad pivot is very small pivot, is called as a coordinate pivot, is together, and then it might be singular, really singular. For example, the elasticity problem, we have 66 degrees of the rigid body. That is completely singular. So in this way, we can factorize even if matrix is not invertible. But in the case when we have to tackle with a very high constant number, this factorization is need to be computed by accurately. But anyway, we can separate the resistance by, in some sense, this is automatically separated into parts by doing factorization. So this is the way to direct solver is applying. So next issue is how to combine or introduce mixed expression arithmetic. The idea is decompose matrix into two parts: union of the easily factorized part, moderate part, and hard part. So easy part is already we got regarding the threshold pivoting. The pivot is controlled by some user-defined parameter, like 10 to the power minus 2. And this strategy is pick up or understand how many jump appears during the pivoting. So if that is less than this criteria, the A11 part is very easy to factorize. So the approximately the constant number of the A11 part is 10 to the power 6. But the other part is much more, sorry, it is not 6. Maybe better to think about it. But what is but actually this is like 10 to the power 12 or something. So A22 part is hard to factorize. So one idea is to use preconditioner. We have to solve the A11 system inverse. The short complement is consists of the A11 inverse A12. But to do that, I have to solve the linear system with multiple right-hand side A12. This system can be solved by row operation, iterative solver. That is one point. In totally, I want to construct algorithm for direct factorization, but internally, I decided to use iterative solver. So because this constant number is very moderate, and if we find a good preconditioner, this iterative solver converges very quickly. And then the way to introduce the preconditioner is to factorize matrix in row operation. Because the constant number is moderate, so row operation is very approximate of the original matrix, part of the matrix. But if we try this on the whole system, if constant number is huge, the factorization by row operation is not enough. But this way is I already decompose into two parts, the moderate part and the hard part. The moderate part is can be factorized in row operation, but solution itself by iterative solver is obtained by higher pressure. That means short complement is still well computed accurately in higher pressure. So short complement S22 could be singular, containing the very huge physical jump plus something numerical defect by kind of the containing a singular system. So I will summarize is the block conjugate general conjugate residual method with preconditioner that is computed by value factorization in row operation. And so this algorithm is intended to keep of the factorization itself, not to improve the solution computed by row operation. And then usually that is iterative refinement technique, try to improve the solution. But this idea is to improve, to keep the algorithm itself is the same accuracy using the row operation. And that is operation is used for faster computation and also for the smaller memory footprint. This is the idea. And also the symmetric pivoting is good for to fit this framework because on the closed loop subspace method, we have to compute sparse matrix times some sparse matrices. So this is very easy to operate it if the pivot is symmetric. Just I can replace some part as 0. So test function and then unknown function share the same indices, same group of indices. Very easy to manipulate with kind of symmetric pivoting. And next step, I have to little bit explain about the difference with iterative refinement and the closed subspace method. So iterative refinement is very common technique for to use the mixed expression arithmetic, but I found this is a kind of the similar way to in closed subspace, but less efficient way. So first I have to look at what is the iterative refinement we do. So the first linear system is AX or B, and solution is obtained by row operation. X0 is by solution by row operation, and residual is obtained. And we would like to improve the residual, the system of the X0 solution, adding to solving the residual system. So E0 is something compensate variables, so solved by row operation arithmetic. Now here is Q is the same system, but in row operation. So we can see what is the residual in the next first step. R1 is B minus X1, and this is calculated like this way. I minus AQ1 inverse RZ. And also the solution, the first solution is X1 is the accumulation of this update. So this is also written by this way, X0 plus Q inverse 1. And then I can apply the same thing in the second stage. So just I need to skip faster. And this is the R2 is expressed by this operator 1 minus AQ inverse squared. And then you can see the A is the original matrix, and then Q is the factorized matrix in row operation. This is almost 1, but of course the difference of the numerical error. So this is not 1. So this is something of the understanding of the iterative refinement in operator sense. And also I continue on the n step. This means R0 is computed as this. R0 is computed as this. R0 is computed as this way. So this is we can see this is belongs to closed subspace R0, and then the multiplicator of AQ inverse, and then solution is the written like that. It's binomial coefficients. So solution is found in closed subspace, but not using Galerkin orthogonality. That means if we use Galerkin orthogonality, is any kind of the closed method can faster than this one. But this idea is I employ not iterative refinement. I prefer to use DCR method. DCR method is just a kind of extension of the conjugate, not by conjugate method, but extension of the conjugate gradient method, adding to orthogonality to previous such vector. Always it's like that. But here we are starting from X0, and then inside we have several such vectors that is accumulated, different from CZ method. CZ method only can keep, we need to keep the previous vector, but here we have to keep all the previous vectors. And then the orthogonality is computed by something the weighted node. So I'll summarize what happened here. Solution also found in closed subspace, and different from the iterative refinement. Residual is also to such space, but this is has the weight, not the different, not same as gemless or FOM fully orthogonal method. This weight is slightly different, but anyway, this orthogonality is much how to say the proper than the iterative refinement. In the iterative refinement is also the considered a special case of DCR method. So if we set the some parameters, alpha, beta, is the kind of the parameter for orthogonality. If we put alpha is 1 and all beta is 0, this can coincide with the iterative defining. But this is much more faster way, and I'll show the in 2 slides. But here is I thinking about the single right hand side. But as I said, I would like to compute short complement. So is I have to use the block version. And then so this way I need to solve the against the B block matrix B, and then but the algorithm is completely the same. So this is a convergence history of the to compute the short complement by using the iterative definement and GCR and the block GCR. And this is this horizontal is the iterative number, vertical is the residual. So purple is by iterative definement is converged, but stopped here above 10 to minus 14. But due to the round of error, but GCR can converge faster, and also block GCR is much faster because of the it consists of the based on the much more wider closed subspace. So this is the way to compute the short complement inside of the direct solver. I can use this kind of iterative solver because the residual is I think it's 10 to minus 17 about 4 times iteration. That is almost the exact solution. So actually, this I almost 5 minutes to finish. But this is one example to solving of the matrix from matrix market. So here is the control number is 10 to power, sorry, lambda 10 to power 11. And then moderate part of the control number is 10 to power 3. Because this shows the eigenvalue distribution. Matrix is symmetric, so this is SBD, but actually shows the eigenvalue distribution. Only the small part is very bad. The almost part is very easy to solve. So the moderate part is control number 10 to power 3. So this part could be factorized by the single precision, and also, but in total, that is the control number is higher. So I have to cannot neglect every computation of the double precision arithmetic. So the mixture of double precision and single precision can retain of the error and the residual. And but unfortunately, ratio of the hardware of the speed double and float is only 2 times different. So I have another things to using the iterative solver to compute short complement. No, the time speed is not much become faster, 0.5 against 0.4. But anyway, mixed arithmetic precision can save the time, but keep the same accuracy. If I do the all computation by single precision, so this part cannot be resolved by single precision. So solution is become suffer the large error. So next one is just using a PFM. So I think about the Stokes equation with full Neumann boundary condition. Here we have 6 degree of 6-dimensional kernel. I put the whole full Neumann boundary condition. This is artificial, sorry, but this corresponds to the rigid body mode. And I use the stabilized finite element. And here by sorry. What? Yeah. So here is the control number is in total the 10 to the power 19 because of the 6 null pivot. But actual control number is 10 to the power 7 because due to the double experience. And the usage of the double pressure, my solver can find the 66 rigid body is detected, and the computation time is 33 seconds, and memory is used 17 gigabyte was used. And by mixed precision arithmetic, also 6 degree freedom is detected, and the computation time is around 22, and the memory footprint is not half, but very much more smaller. But by using single precision arithmetic, due to high constant number of the 10 to the power 7, excluding even if excluded the exclusion of the kernel, is this control by higher that we cannot deal with the single precision. So in this case, the kernel is not detected. So this is a good way to understand. And the last one is example by semiconductor. Here is the result by quadruplication is computation by quadruplication is necessary, and the condition number is just 10 to the power. This is the condition number is 10 to the power 22 in the invertible part. Here we can see the kernel is 1, everything detected, but the error is good for by mixed arithmetic, mixed expression arithmetic. And the computation time is here is very we have out of game because the double is much slower than double, 25 times slower. So sorry, the next one is the final summary. So here I showed the mixed expression arithmetic that can bring us to faster computation and also smaller memory footprint. I will provide this as a part of FFM in future. Thank you very much for your attention. So I will take some time.
Time for one question.
So when you do the factorization, do you automatically decide whether you can switch to mixed precision, or do you need to tell before doing the factorization, okay, this is the problem where I know that there will be the top part and the middle part, and you can do the mixed precision? Is
Okay.
it something that you decide a priori, or is it something that is decided by your software?
That's a good question. So usual case, I can trust a software and a mixture of the single precision and double precision. But last example I showed is has very high conditional